17E. So number 1, a coin is tossed 16 times. The number of heads is like the sum of 16 draws made at random from replacement from which of the following boxes? 1, 2, or 3? 2. Now remember, up until this point, we have been adding the numbers in the box to create a sum. But if you want to count how many times a number happens, then you put a 0 every time the number doesn't happen, and a 1 every time the number does happen. So we can turn H's and T's into 0s and 1s. And then we just do exactly the same thing that we've always done. So for heads and tails, we would pick 2. 0 would represent tails because we don't care about tails, and 1 would represent heads. So the number of heads would be around 8, give or take. Well, we would need the SD of the box, which is going to be 1/2. And then we take 1/2 and we multiply it by the square root of 16, which is 4. So the answer is 8 plus or minus 4.
Plus or minus 2. Half of 4.
Oh, half of 4. Sorry. Plus or minus 2. You're right. So it would be 1 minus 0 times the square root of 1/2 times 1/2, which ends up being 1/2. Multiply that by the square root of 16 is 4, so 2. So we would expect the number of heads to be 8 within 2. 68% of the people would be between 6 and 10. Okay? All right, 100 draws are made at random with replacement from that box. What is the chance of getting between 8 and 32 tickets marked 5? So we have to build a new box. Okay? And how many chances are there in the box to win? If we draw 5, we win. So 1 copy of 1. Because we can only get 5 1 in 5 times. So every time we get a 5, we add 1 to our total. Right. And then we'll have 5 copies of 0. So we'll win 1/5 of the times. Wait, are there only 5? Oh, sorry. I thought it was a dice. I'm sorry. So 4 times 0. Now we need the average of the box. No, not the SD, the average. So it's 1 plus 4 times 0, which is 1, and there are 5 tickets in the box. So the average of the box is 1/5. I just added all the tickets together. 1 plus 0 plus 0 plus 0 plus 0 divided by 5 is 1/5. Now, how many draws are we going to make? 100. So I times that by 100, and I get 20. What does 20 mean? 5s. So for every 100 draws, we expect 20 5s. Okay, now we need to find the SE. Well, the SD of the box, the shortcut is 1 minus 0 times the square root of 1/5 times 4/5. So the square root of 1/5 times 4/5 happens to be 0.4 or 2/5. So this is 0.4. Now I multiply that by the square root of 100. It's so 4. So we expect 25s, give or take 4 5s. But the question wants to know, what's the chance of getting between 8 and 32? So we need to draw our normal curve. The middle is going to be 20, right? And we need to go over to 8 and up to 32. What's the distance there? 12. Okay, what's the distance here? 12. So we're 3 SDs to the right and 3 SDs to the left. And we know that it's going to be 99.7. Okay, and you could do, if you forget the memorized rule, you could just do shade norm, and you're going to end up with 99.7. Or you can actually look up, you could look up 3 in the z-score table, and if you go to 3 in the z-score table, z-score is your difference divided by your SE. Yeah. Okay, good job. According to the simple genetic model, the sex of a child is determined at random, as if drawing a ticket at random from the box, male and female. What is the chance that the next 25,000 births, not counting twins or older or other multiple births, more than 1275 will be females? So we need to build a new box. What goes in the box? 1, 0, and 1, 1. Does it have to be 1, 0, and 1, 1? It could be 2 zeros and 2 ones, or 100 zeros and 100 ones. So, right there, there's a 50-50 chance. And every time, so this would be male and female. Every time female happens, we add 1 point. And every time male happens, we add 0. Okay? So the average of the box is 0.5. Multiply that by 25,000 kids. We would expect 12,050 of them to be female. Everybody okay with that? The SD of the box is 1 minus 0 times the square root. Are we confused over here? Well, sorry, where are you confused? Okay. Okay, pay attention. Yeah. Okay, so 1/2 times 1/2. The formula is big number minus small number times the square root of the fraction of big times the fraction of small. And that's going to end up being 1/2. So this is how many people we're looking at. The question says 25,000. 2,500. Thank you. So this is 1/2. What does that mean? In the box, the numbers in the box, on average, are 1/2 of a unit away from the average of the box, which is 1/2. Right. So the SD of the box is 1/2. I multiply that by the square root of 2,500, which is 50. So 1/2 times 50 is 25. What does that tell me? So we expect in the next 2,500 births, this many of them will be 50, give or take, or be female, give or take 25 kids. Female, 25 kids, yeah. So the question is asking, what is the chance that we end up with more than 1275? So I'm going to put 1250 right in the middle. 1275 is 1 SD. And are we going to shade left or shade right? Right. Not 2. So we're going to clear our draws. So shade norm. Shade norm. What do I put for my lower bound? 1. What do I put for my upper bound? 5. It won't be 33. It's going to be half of 33. Oh, it didn't work. It's going to be half of 33%. So we ended up with 15.8. Why is it half of 33%? Well, that 68 rule is the middle. So if we subtract off the middle, we end up with 2 equal tails. And we have to divide it by 2 to find that other tail. Okay. Number 4. This exercise and the next are based on Carrick's coin tossing experiment. For example, in tosses 1 through 100. Shh. Do we need new seats? Quit it. Okay. The observed number of heads was 44. The expected number was 50. So the chance error was -6. So fill in the blanks. So for 101 to 200, the chance error is going to be +4. Okay. For 201 to 300, what's the expected value? 50. And then from 301 to 400, how do we find the observed value? It's in the table on the previous page. So go to 301 to 400, the number of heads, 53, expected value, 50, chance error, +3. And then the standard error is going to be the same for every one of them. How do we find the standard error? Well, it's this box, 1 copy of losing and 1 copy of winning. So the SD is 1/2. Okay, we multiply that by the square root of the number of draws. And I get the square root of 10, the square root of 100 is 10, times 1/2 is 5. So the SE is 5. And it's 5 for all of them. They all have the same expected value and the same standard error. Okay. How many of the counts in table 3 should be in the range from 45 to 55? 68% of how many times was the game played?
Wait, the answers say that the expected value is 50.
Right, and the standard error is 5. So that, yeah, the expected value is always 50 and the standard error is always 5. Okay? So, how many times did he play the game? 100 copies of 100. So how many of them do we expect to be within 1 SE? 68 of them, right? 68%. So 68 out of the 100 plays should land inside 1 SE. All right, 6. A coin is tossed 10,000 times. What is the chance that the number of heads will be between 4850 and 5150? So, what is the expected value? 5,000. And we know that the SD of the box is 1/2. How do I find the standard error for 10,000 draws? I take 1/2 and multiply that by the square root of 10,000. And I end up with 50. What does that mean? That's the SE. Okay? So, over on the left we have 4850. And on the right we have 5150. How far is that gap to the left? 150. In terms of the SE, it has a z-score of -3. And then how far to the right do I need to go? 150, which in terms of the SE is plus 3. So in this case, it's 99.7. 99.7% of everybody who plays the game 10,000 times will have the number of heads between 4850 and 5150. All right. B. A coin is tossed 10,000 or 1,000,000 times. What is the chance that the number of heads is between 49500 and 501? Same thing. So we still have an SD of 1/2. Normal curve. We put 1,000,000 in the middle. Okay. And now my SE is now 1/2 times the square root of 1,000,000. So the square root of 1,000,000 is 1,000 times 1/2. I get an SE of 500. So how many SEs to the left until I get to 498,500? That would be 1,500 divided by 500 is 3 SEs. It's the same. Okay. Now the interesting thing here is when we jumped from 10,000 to 1,000,000, we multiplied our expected value by 100, but we only multiplied our SE by 10. And remember, the chance error is supposed to go up, but the percent error is supposed to go down, which is what happened in this case. All right. 50 draws are made at random with replacement from the box 00111. There are 33 ones among the draws. The expected number of ones is, so if we did 50 draws, it would be 3/5 of 50, which would be 30. The observed number is 33. The chance error is plus 3. And the SE we'll need to calculate 1 minus 0 times the square root of 3/5 times 2/5. So 3/5 times 2/5. So the SD of the box is 0.489, and now we need to multiply that by the square root of 50. And we get 3.46. The SE is 3.46. Okay. A computer program is written to do the following job. There is a box with 10 blank tickets. You tell the program what numbers to write on the tickets and how many draws to make. Then the computer will draw that many tickets at random with replacement from the box, add them up, and print out the sum, but not the draws. This program does not know anything about coin tossing. Still, you can use it to simulate the number of heads in 1,000 tosses of a coin. How? Put in 5 zeros and 5 ones and do 1,000 draws. That's all you need to do. Okay? Do you really need 10 tickets? No. As long as there are just as many zeros as there are 1, then the outcome is not going to be any different. You could do 1 0 and 1 1 and you'll get the same result. Okay? A die is rolled 100 times. Someone figures the expected number of aces as 100 times 1/6, and the SE as the square root of 100 times the square root of 1/6 times 5/6, and ace is 1. Is this right? So we got the expected value. You have a 1 in 6 chance of winning times 100 draws. Okay, the SE has to be the square root of 100 times the SD of the box. And inside the box, we have 1 1 and 5 zeros. So 1 minus 0 is 1 times the square root of 1/6 times 5/6. So yes, it works.